Hey guys, we are dealing with force, density, and pressure, and I think this is going to be lesson 4. Where basically in lesson 4 we are going to give more examples under moments and equilibrium, or moments and principle of moments and torque. In lesson 3 we talked about the principle of moments, we talked about moments in general, we talked about a couple. And therefore, in lesson 4, I just want us to give more examples. Most of the examples here are going to be very simple and they are going to relate to what you studied in IGCSE. But the best examples, you'll find them in the solved past paper questions. Do not forget to check out the solved past paper questions for you to get a lot of confidence with these questions in paper 2 or in paper 1. I have both solved past paper questions in paper 1 and then in paper 2, so you can always check them out. Okay, let's go to the first question. We just want to gain confidence in determining moments, calculating the torque of a couple, and so on and so forth. Okay, question number 1, calculate the torque. So here we have two equal forces which act in opposite directions. Therefore, they constitute what we call a couple, and we notice that their lines of action will never meet. So since they are only two and they are equal and opposite, the moment of a couple or the torque of a couple is the product of one of the forces and the perpendicular distance between the two forces. So the torque of a couple, which I'll call ta, is going to be the product of one of the forces, which is going to be 4 newtons, times the perpendicular distance between the two forces. This is going to be 0.2 meters. So this will be times 0.2 meters. And I think this gives us, I think this should be 0.8 newtons. So that would be the moment of a couple, 0.8 Newton meters, not newtons, because this is newtons and this is in meters. So that is going to be the torque. Product of one of the forces times the perpendicular distance between the two forces. Alternatively, you could divide this into 2 and you find the moment due to the first force plus the moment due to the other force. Because they are both causing a clockwise moment, it means they will cause a rotational effect which is going to be clockwise. So the torque here is 0.8 Newton meters, and this is going to be clockwise. What is happening? 0.8 Newton meters, and this is clockwise. So that is the torque of that couple. Then characteristics of bodies under the action of a couple, because we saw in lesson 1 that these are two equal but parallel forces. So before we do more examples, I want to remind ourselves about the characteristics of a body under the action of a couple. Number 1, remember the resultant force must be 0. That's number 1. The two forces are equal but opposite, so the resultant force must be 0. Number 2, the turning effect of the forces will cause a rotation. The forces must cause a rotation. When you look at their orientation on the object, they should be able to cause a rotation. So the turning effect must cause a rotation. These two forces must act in the opposite directions, of course on the same body but in opposite directions. And their lines of action can never meet. What do I mean? If I prolong this line here of action of this force, and I prolong the line of action of the other force, these lines should never meet. That's what a couple should be. Also note that the moment is a vector quantity, or moment or torque is one of the vector quantities that we discussed in unit number 1, which is physical quantities and units, or topic number 1, which is physical quantities and units. So the moment and the torque or torque of vector quantities, as their magnitude and direction are already specified. That's why many times I'll be saying clockwise or anti-clockwise. So every time you deal with moment, think about the direction, although in some cases or in most cases the direction may not be asked in an exam. Okay, question number 2. A uniform meter rule. Uniform in the sense that its weight acts at the center or at the midpoint. A uniform meter rule balances horizontal on a knife edge placed at 60 centimeters when 2 Newton weight is suspended at one end. With the help of a diagram, show at which end of the meter rule the 2 Newton weight must be suspended. So because it's a uniform meter rule, its weight must be at the midpoint. So if the weight is at the midpoint, then it is suspended at the 60 centimeter mark, because the balance is on a knife edge at the 60 centimeter mark, when a 2 Newton weight is suspended at one end. So from the center to the 60 centimeter mark is going to be 10 centimeters, because the weight of the meter rule is 50 centimeters. Is at the 50 centimeter mark. So it means the 2 Newton is going to be placed on the other side. So the diagram would look something like this. So the 2 Newton is going to be placed the other side if the pivot is at the 60 centimeter mark. So the distance of the weight from the pivot is going to be 10 centimeters, which is 0.1 in meters. And the 2 Newton is going to be placed on the other side, which is 60 centimeter mark to 100 centimeter mark. This is going to be 40 centimeters, which is the same as 0.4 in meters. So calculate the weight, the mass of the meter rule, the reaction R at the knife edge. Take G to be 10, although I will not take G as 10. I will take G as 9.81 meters per second squared. So taking moments about the pivot, the weight W times the perpendicular distance, which is 0.1, is equal to the force of 2 newtons times the perpendicular distance, which is 0.4. So this gives us, or implies, that the weight W is equal to 2 times 0.4 divided by 0.1. So which is 0.8 divided by 0.1, which I think is 8.0 newtons. So that is the weight W. Then the mass of the meter rule. So if W is the weight, of course the mass is the weight divided by G. So which will be 8 newtons divided by 9.81. So the weight is going to be 8 divided by 9.81. The mass is going to be 8 divided by 9.81, which will give us 0.82. 0.82 kilograms. Then the reaction R at the knife edge. Of course, the reaction R is, we are going to use the first condition for equilibrium. The resultant force equals to the, so total forces upwards should be equal to total forces downwards. So R is going to be W plus 2 newtons, which will be equal to 8.0 plus 2, which gives us 10.0 newtons. So that will be R. As simple as that. Okay, so the answers, of course, I think these answers were calculated using 10, but I would prefer to use 9.81. A uniform half meter rule. So this is a half meter rule, and a half meter rule is 50 centimeters. Is freely pivoted at 20 centimeter mark, and it balances horizontally when a weight of 10 newtons is suspended at the 40 centimeter mark, at the 4 centimeter mark. Draw a sketch diagram showing all the forces acting. So I'll sketch a half meter rule here. And it is pivoted. Let this be the 0 centimeter mark. Because half meter rule is 50, let's say 20 centimeter mark is somewhere here. So this is 20 centimeter mark. This is the 50 centimeter mark. And it balances horizontal. Because it's uniform, its weight is going to be at 25. So let's say 25 is just after 20. So this is going to be the weight of the meter rule at 25. So this is at 25 centimeter mark. This is at the 25 centimeter mark, which means the distance here is going to be 5. That distance is 5 centimeters, which is 0.05 meters. So of course, this is going to cause a moment which is clockwise. Then anti-balance is horizontal when a weight of 10 newtons is suspended at the 4 centimeter mark. So this should be put at the 4 centimeter mark. Let's say 4 centimeter mark is here. This is where we have 10 newtons. This is at the 4 centimeter mark. So the distance here is, the distance from the pivot to that point is going to be 20 minus 4, which is 16 centimeters or 0.16 meters. And this will be anti-clockwise. So for equilibrium, the sum of clockwise moments is going to be equal to the sum of anti-clockwise moments. So we shall say that W times the perpendicular distance, which is 0.05, should be equal to 10 times 0.16. So W is going to be 10 times 0.16 divided by 0.05. So it's 10 times 0.16 divided by 0.05. So this gives me 32 newtons. So W is 30 newtons. The weight of the meter of the half meter rule, this is half meter rule, is 32 newtons. And then the reaction at the knife edge. Of course, the reactions, the total forces downwards should be equal to the total force upwards. So if the reaction is acting at the knife edge upwards, so R is going to be the weight W plus 10, which will be 32 plus 10, which gives you 42 newtons. A uniform plank of weight 100 newtons with a bucket of weight 40 newtons on it is supported by its trezors as shown by two trezors as shown below. What force does each trezor exert on the plank if it is in equilibrium? So if it is in equilibrium, let's first sketch a force diagram. So whatever this, we are going to call this trezor A. I'll call this one trezor B. And of course, there is a weight here which acts vertically downwards. And this weight, the weight is 40 newtons, so that is 40 newtons. It is a uniform plank of 100 newtons. So because it's uniform, its weight acts at the midpoint. So we look for the midpoint and we shall put there 100 newtons. So these are the forces acting. Of course, there's a force here from the plank. I'll call this one X. There will also be a force here. I'll call this one Y. So the question is, what forces does each trezor exert on the plank if it is in equilibrium? So if it is in equilibrium, in the first place, the total forces upwards should be equal to total forces downwards. That's number one. Number two, the sum of clockwise moments about a given point will be equal to the sum of anticlockwise moments about the same point. So since the body is in equilibrium, the moments must balance and the forces in opposite direction must also be equal. So the free body diagram, or a diagram which shows only forces, could look like this. So we have 1 meter, then the plank was of length 4 meters according to the diagram, and since it is uniform, this is at 2 meters, so the 100 newtons at 2 meters. So I have to choose somewhere to take moments. So I'm going to take moments about, okay, for the first condition, I have that X plus Y equals to 40 plus 100. That is condition number one. The resultant force should be equal to 0. That is, X plus Y should be equal to 140 newtons. That is condition number one. Resultant force should be equal to 0. That is, total forces in opposite directions should be equal so that they cancel out. Then if I take moments about, say, I'm going to take moments about A. So moments about A. So I'm taking moments about A. So the 40 newtons is going to cause clockwise moments, 100 newtons causes clockwise moments. X will have no moment, Y will cause anti-clockwise. So perpendicular distance for Y is 2 plus 1 plus 1, which is 4. So I will say Y times perpendicular distance, which is 4 meters, should be equal to 40 times 1 plus 100 times 2. So sum of anticlockwise moments should be equal to the sum of clockwise moments. So it means y or 4y is going to be equal to 240. That is 40 plus 200. So it means y is going to be equal to, I think that is 60 newtons. So that is y. And then if y is 60 newtons, it means x, remember x plus y is equal to, x plus y should be equal to 140. So x is going to be 140 minus 60, which gives you, I think this is 80. I think that is 80 newtons. So the question was, what force does each tracer exert on the plank? So if tracer at A exerts a force X, it exerts 80 newtons, and if a tracer B or at B exerts a force Y, it exerts 60 newtons. So these are going to be answers to this question here. Okay, so since the body is in equilibrium, the moments must balance and the forces in opposite directions must also balance. So that's what I've just done here. I considered resultant force equaling to 0 by summing up the forces in opposite directions, and I took moments about point A. You could also take moments about point B, and I'm very certain you would get the same answer. Calculate the moment of the force about the fulcrum when a petty dog of mass 10 kilograms is at a distance of 1.2 meters from the fulcrum of the seesaw. So calculate the moment of force about the fulcrum when a pet dog of mass 10 kilograms. So it means the force is going to be equal to the weight, which is equal to mg. So this will be 10 times 9.81. So which is going to be 98.1 newtons. So that is the force. And its perpendicular distance is 1.2 from the fulcrum. So it means the moment, which is going to be tau, is the product of the force 98.1 times perpendicular distance 1.2. 98.1 times 1.2. So this is equal to 117.72 Newton meters. Of course, this is approximately 120 Newton meters to two significant figures. In the figure below, calculate the moment of the force about the end A. I think we have done this as an example in lesson 2. So I will just remind you that you try to find the perpendicular distance. So if I try to find the perpendicular distance from the pivot, I must draw a line which makes 90 degrees the line of action of the force from the pivot. So this is the perpendicular distance, and it is in the opposite of the angle 65. And this is in the hypotenuse. We just change this to meters, 0.45 meters. So opposite hypotenuse, that is, I think that is sine. Sine of 65 is equal to the opposite over the hypotenuse, which is 0.45. So the perpendicular distance is 0.45 sine of 65. So it means the moment is the product of the force, which is 30 newtons, times the perpendicular distance, which is 0.45 sine of 65, which I think it is 12.2 Newton meters as required. A student applies a force of 10 newtons to the hand of a door which is 0.80 meters from the hinge of the door. Calculate the moment of the force. So the perpendicular distance is 0.8 and the force is F. They gave us, so the force is 10 newtons. So the moment is simply the force times the perpendicular distance, which gives us 8 Newton meters. So that is an easy question. The torque produced by a person using a screwdriver is 0.18 Newton meters. So that is the torque. This torque is applied to the hand of diameter 4 centimeters. Calculate the force applied to the hand. So it is applied to the hand of diameter 4 centimeters. So let's say this is there is a torque applied to the handle of diameter 4 centimeters. Calculate the force applied to the handle. So we want to find the force F. So we know that the torque, because this is a couple, the torque produced by a person using a screwdriver is this. Okay, so this is just torque. So torque is equal to the product of force times the perpendicular distance. So they say this torque is applied to the handle of diameter 4 centimeters. So assuming 4 centimeters is the perpendicular distance from where the turning point is taking place, then we shall simply say that 0.18 equals to the force times the perpendicular distance, which is 0.04. And I think 4 divided by, so F is going to be 0.18 divided by 0.04, which I'm very certain this is going to be 4.5 newtons. Calculate the torque produced by two forces, each of magnitude 30 newtons, acting in opposite directions with their lines of action separated by a distance of 25 centimeters. So it means that now this is a couple. The first one is not a couple, this is a couple. So if this is a couple, then we know that the moment or the torque of a couple is the product of one of the forces times the perpendicular distance between them. This is the same as 0.25. So I think this gives us 7.5. 30 times 0.25. So this is 7.5 Newton meters. Determine the torque produced by the couple below. So we have two equal forces acting in opposite directions. All we need is the perpendicular distance between the two forces, which is going to be 0.4 meters. So the torque of a couple is equal to the product of one of the forces times the perpendicular distance between the two forces, which is 0.4. And I think this gives us 6 Newton meters. Alternatively, you can find the moment caused by the first force, which will be 15 times 0.2, plus the moment caused by the second one, which is also 15 times 0.2. But this is clockwise, this is clockwise. So the resultant moment is going to be clockwise. So when you sum up this and this, I think it's the same as getting 15 times 0.4, which is 6 Newton meters. The diagram below represents a uniform beam which is in equilibrium. The block resting on the beam has a mass of 2 kilograms. A rope is holding the system in equilibrium. Calculate the magnitude of the tension T in the rope. So we want magnitude of the tension T in the rope. So remember, you must learn some resolving here. So this is the equilibrium, which means the resultant force must be 0. That's number 1. And calculate the magnitude of the tension T in the rope. So I'm going to take moments about the pivot here. So W is causing an anti-clockwise moment because it's pulling the beam downwards on the left-hand side. And the tension T has two components. One component will be acting horizontal, and this component will have no moment because its line of action goes through the pivot. So there is no perpendicular distance. In that case, this is going to be T. Of course, this is T sine of 40. Remember I said if the vector if the angle is between the vector and the direction you are resolving, it is cos. Elsewhere, it is going to be sine. So t in the vertical is t cos of 40. So t cos 40 is going to cause a clockwise moment. Of course, for equilibrium, t cos 40 should be equal to w sine, should be equal, t cos 40 is the force acting in the vertical times this perpendicular distance is going to cause clockwise moments, should balance with the anti-clockwise moments given by W. But the block resting on the beam has a mass of 2 kilograms. So this is 2 kilograms. So the mass, the W here is going to be 2 times 9.81 in newtons. This distance is going to be 0. But of course, even if I don't change the units, but you can still change, but the units will cancel out. So taking moments above the pivot, the sum clockwise moments will be t cos of 40 times the perpendicular distance, which is say 25 or 0.25 meters, should be equal to 2 times 9.81 times the perpendicular distance, which is 0.5. I'll just press my calculator. So this is 2 times 9.81 times 0.5 divided by 0.25 cos of 40. Remember to learn how to resolve because it's very important. So this is giving me 51.2. So T is 51.2 newtons. That is the tension. Okay. The diagram in the figure shows a uniform half-meter rule suspended at point P. The mass of the rule is, so you have to find the mass of the rule. It is a uniform half-meter rule. That means its total length is 100 centimeters. I mean, it's 50 centimeters. It is a half-meter rule. So if this is 5 centimeters, I will say this is the 0 centimeter mark, 5 centimeter mark. Because it's a uniform half-meter rule, we can assume that its mass acts at the midpoint. So this is going to be 25 centimeter mark. So that this is 50 centimeter mark. So the distance from the turning point is going to be 25 minus 5. This is going to be 20 centimeters. So M is causing a clockwise moment, 0.1 is causing anti-clockwise moment. So if the object is uniform, the center of mass is the center of gravity is the same as the center of mass. So taking moments about point P, so we shall say M times the perpendicular distance, which is 20 centimeters, should be equal to 0.1. Of course, this is in kilograms, times the perpendicular distance, which is 5 centimeters. Of course, the centimeters cancels out. So M is going to be 0.1 times 5 divided by 20. 0.1 times 5 divided by 20. So this gives us M as 0.025 kilograms. So that is M. A uniform wooden beam of weight W. So because the beam is uniform, its weight is at the midpoint. Is pivoted at a distance a fifth or 1/5 of its length from end A and kept in equilibrium by applying a force of 30 newtons as shown in the figure. So this distance is most likely going to be a fifth. So let the length of the beam be L. So this is going to be 1/5 of L. A fifth of its length from the end A. So it means the whole of this distance here is going to be a half L. This is going to be a half L. So which means this distance here is going to be a half L minus a half L minus 1 over 5L is going to be equal to LCM is going to be 10. 10 divided by 2, 5L minus 2L. So that gives us 3 over 10L. So this distance is 3 over 10L. Okay, so the question is the force exerted by the pivot on the beam is, so we want the force here. Let me call that F. So from the first law, the first condition, F is going to be equal to 30 newtons plus W. From the second condition, conservation of, principle of moments, W is going to cause clockwise moments, 30 newtons is causing anti-clockwise moments. So W times the 3 over 10 L should be equal to 30 times 1 over 5 L. So L cancels out, of course, and making W the subject, W is going to be 30 divided by 5, that is 6 times 10 divided by 3, which gives us, I think that is 20 newtons. So it means that F is going to be 30 plus 20, which is equal to 50 newtons. So F is going to be 50 newtons. I hope I subtracted correctly. A half. Yeah, that is correct. A uniform road 100 centimeters. The road is uniform. Its weight must be at the midpoint, or its mass must be at the center. It's pivoted at the 90 centimeter mark. Balances horizontally when a mass of 200 grams suspended at the 100 centimeter mark, as shown in the figure. The mass of the rod is, so we want to find the mass of the rod. So because this is uniform, it must be at 50. Let me look for 50. Let's say 50 is somewhere here. This is where we expect the mass of the rod to act. Let me call it M. And M, because this is at the 50 centimeter mark, since this is a uniform rod of 100 centimeters, this length is going to be 40 centimeters. This length is 10. This is not drawn to scale. So taking moments about the pivot, then M times perpendicular distance, which is 40 centimeters, is going to be equal to 200 grams times the perpendicular distance, which is 10 centimeters. So it means M is going to be 200 grams times 10 centimeters divided by 40 centimeters. So this gives us 2000 divided by 40, which is 50 grams. The figure below shows a uniform meter rule of mass, 0.1 kilograms. It is a uniform meter rule. That means its length is 100 centimeters. And because it's uniform, it means its weight acts at the midpoint. So we have to look for the midpoint, which is 50. That's where its weight acts. So let's say its weight acts here. The weight acts at that point. The mass of the meter is 0.1 kilograms. So it means the weight acts here, the mass also acts here. So here I'll put 0.1 kilogram here, even though it is mass, not force. It balances horizontally when a mass P is hanging at the 95 centimeter mark. So the distance from the pivot to the mass P is 95 minus 80, which is 15 centimeters. And the distance from the center to the pivot is going to be 80 minus 50, which is 30 centimeters. So find P. So I will say P times because P is going to cause a clockwise moment and the mass of the rule causes anti-clockwise moment. So P times perpendicular distance, which is 15 centimeters, should be equal to 0.1 kilograms times perpendicular distance, which is 30 centimeters. So P is going to be equal to 0.1 kilograms times 30 centimeters divided by 15 centimeters. So this gives us 0.1 times 30 divided by 15. So P is going to be 0.2 kilograms. As simple as that. A uniform meter rule, it is uniform and it is a meter. So it means the length is 100 centimeters. Is pivoted at its center shown in the figure. So it is at the center. This is at the 50 centimeter mark. If the rule is in equilibrium, find the value of F. So since it is at the center, it is pivoted at the center. This distance is 50 centimeters. So taking moments above the pivot, F is causing clockwise, 20 newtons causing anti-clockwise. So for equilibrium, the sum of clockwise moments, which is F times 20 centimeters, should be equal to the sum of anti-clockwise moments, which is 20 newtons times 50 centimeters. So F is going to be 20 newtons times 50 centimeters divided by 20 centimeters. So F is going to be 50 newtons. F will be 50 newtons as required. Find the weight W of a uniform meter rule. If a force of 60 newtons at one end balances it as shown, it is a meter rule, that is 100 centimeters. So this is at the 50 centimeter mark. Because it is uniform, its weight acts at the 50 centimeter mark. So the distance here is given as 30. So this causes anti-clockwise moment. 60 newtons causes clockwise. So taking moments about the pivot, the sum of anti-clockwise moment W times 30 centimeters should be equal to 60 newtons times 20 centimeters. So W is going to be equal to 60 newtons times 20 centimeters. Divide this by 30 centimeters. So this cancels out. So I think this gives us, that is 2 times 20, which gives us 40 newtons. So the weight W is going to be 40 newtons, because this is 240. If the meter rule is in equilibrium, when weights 10 newtons, 2 newtons, 5 newtons are attached to it as shown in the figure. Calculate the tension, calculate the Roman 1 tension in the string, Roman 2 normal reaction R at the wedge. So the first thing we need to note is to find the forces which are acting. So this is supporting this at this point. It is a string maybe. And remember, this is a meter rule. That means total length is 100 centimeters. Let us assume that 1 Newton is the weight of the meter rule. So the weight 1 Newton is acting at the center. So the whole of this distance is going to be 50 centimeters, which means if this is 25, this is going to be 20 centimeters. To make it 50, 5 plus 25, that is 30, plus 20, that is 50. Then the whole of this distance is also going to be 50. So that means if this is 30, this is 20, and this is 15. So 30 plus 15, that is 45. So this distance is going to be 5. So that 30 plus 5 plus 15 gives us 50. Okay. So we want to find the tension. So there will be tension force here. Of course, tension will act away from the object. The tension in the string acts away from the object. So I can't find the tension. There are two ways of doing this. I may take moments about R. So I'll say moments about R. Moments about R. So the tension T is causing a clockwise moment. Is the only force causing clockwise moments about R. So I'll say T times the perpendicular distance, which is 5 plus 15 plus 20 plus 25. So that is this is 5 plus 15, that is 20, plus 20, that is 40, plus 25, that is 65. So T times 65 centimeters should be equal to, that is clockwise moments. Anti-clockwise, we have 5 newtons, 1 newton, 2 newtons, 10 newtons. These are pulling the beam in the, anti-clockwise if R is fixed. If R is a fixed point, they are pulling the beam anti-clockwise. So we have 5 times 25. I'm not changing the units because I know the units cancel both sides. 5 times 25 centimeters plus 1 times perpendicular distance, which is 20 plus 25, which is 45 centimeters plus 2 perpendicular distance is 45 plus 15, which is I think 60, plus 10 times 25 plus 20, that is 40, plus 15, that is 60, 60 plus 5, that is 65, and this distance here is 20 because we have 30 minus 10, which is 20. So 20 plus 20, that is 40, 60, 85. So that is times 85. So that is the perpendicular distance from 10 newtons up to the pivot. That is 85. So I have to just press my calculator to find T. I'll just sum up this. The centimeters cancel out on both sides. So the answer would be newtons. 5 times 25 plus 45 plus 120 plus 850 divided by 65. So this gives us T as 17.5 newtons. So T will be 17.5 newtons. Of course, for the normal reaction, it will be the sum of the normal reaction force acts at the pivot. It is going to be, I'll call this one force at R. So the force at R acts upwards plus the tension which also acts upwards should be equal to the sum of the forces downwards, which is 10 plus 2 plus 1 plus 5. So it means the normal reaction FR is going to be 10, I think this is 12, 13, 18, minus 17.5, which is going to be 0.5 newtons. So that is 0.5 newtons as the reaction at R. A uniform beam of weight 2.5 newtons is pivoted at its midpoint. That means it is pivoted at the center. As shown in the figure below, the beam remains in equilibrium when force R and S act on it. If R is 5 newtons, so this one is 5 newtons, find S. So because, and the reaction at the pivot. So because it is in equilibrium, S is causing clockwise moments, R is causing anti-clockwise moments. So taking moments about the pivot, clockwise moments should be equal to anti-clockwise moments. So I'll say S times 0.6 should be equal to R times 0.3. Remember, R is 5 newtons, so S is going to be 5 times 0.3 divided by 0.6. So S is going to be equal to 2.5 newtons. Then find the reaction at the pivot. So the reaction acts vertically upwards on the beam. So the reaction is going to be R plus S, which will be 5 plus 2.5. The reaction is going to be 7.5 newtons. So that will be the reaction. The rod PQ is horizontal and in equilibrium. Draw a vector triangle to represent the forces acting on the rod and determine the magnitude and direction of X. Okay, I don't have enough space, but I'm going to write to try and reutilize this space. So for vector triangle, you have to fix one of the vectors and then change and then add the other vectors. So I can fix this vector here, the weight vertically upwards, and then I can start with the 40 Newton force, 29 Newton force, and on its head I can add the weight, which is 50 newtons downwards, and on the head of 50 newtons I must add, because 50 newtons is bigger, so I can make it longer. Then on that I should add X without changing the direction of X. So this will be X. So it means my vector diagram could look like this. Draw a vertical line for the weight of 50 newtons. Then put a force X, and then add the other one of 29 newtons. So this is 50 newtons. We can predict the angles, of course. We can predict some of the angles, I think. If I take this further, this angle here is 60. The angle between X, no, this angle here is 60 between the horizontal and that, okay? If I draw a vertical line here going downwards, this angle here is going to be 30, and this angle here is the same as this angle, so this is 30. So I now know this angle as being 30. Because if I draw a vertical line going downwards, remember this makes 90 degrees with the horizontal. So if this is 60, the other one is 30. Therefore, this angle here is the same as this one, so this angle is 30. And if I have the angle between two vectors joined head to tail, I can use a Pythagoras theorem to find the resultant. But alternatively, you can use a vector triangle. I will not draw this with to scale. I'll just calculate and see if that is true. So I want to find x. So x squared is going to be equal to 29 squared plus 50 squared minus 2 times 29 times 50 cos of 30. I'm using the cosine rule. You can use a scale diagram where you first draw a vertical line. You can choose a scale of, say, 10 newtons. You can say 1 centimeter representing 10 newtons. So you draw in the vertical, you draw 5 centimeters. In the other one, you draw 2.9 centimeters to represent 29 newtons. But let me check with the cosine rule. So x is going to be the square root. So I'll just say 29 squared plus 50 squared minus 2 times 29 times 50 cos of 30. then square root. So this means x is equal to 28.8, which is approximately 29 newtons by the cosine rule. So for the cosine rule, you must know the angle between the two vectors after joining them head to tail. That's why from this triangle here, 50 newtons downwards, x in that direction, I was able to establish this angle here from this diagram here. When I draw the vertical line, it is parallel to the weight downwards. But then if this angle to the horizontal is 60, and this is a vertical line which makes 90 degrees with the horizontal, the other angle is 30 degrees. And if that is 30, the other one is also 30 because I think these are alternating angles. So that's why I came up with this as 30 degrees. You can draw this triangle to scale, and I think you will get almost the same answer. Then determine the magnitude and direction of x. Of course, direction, we can state it in terms of the angle. Either the angle it makes with the vertical, it could be this angle here, it could be that angle here. Of course, if you use, I think because this is less than 90 degrees, you can use sine rule. 29 over sine of this angle here should be equal to x over sine of 30. Alternatively, if you have used the scale diagram, just put here a protractor and measure that angle, and I think it should be approximately 60. But even then, because you have already seen that this magnitude is the same as this one, then this should be an isosceles, not 60, it should be 30. This angle here should be 30. I think this is the one which is going to be, if this is the horizontal, this is the one which is going to be 60 to the horizontal. This will be 30. Because if this is 29 and this is 29, it means these are equal in length. So it is an isosceles triangle where the angles here are going to be equal. If this is the same as this, the angles are going to be equal. So theta is 30, so the angle to the horizontal is going to be 60 degrees. Okay, so you can try that using a scale diagram. Show that the upward forces equal downward forces. So the upward forces, you just resolve upward forces. Downward forces is 50. So let's consider the upward forces. I will resolve 29 to the vertical to be 29 to the vertical to be sine of 60. Then the other one, x is also 29, making an angle of 60 degrees to the horizontal. So it will also be plus 29 sine of 60, which I think is going to be 29 sine 60 times 2, which is equal to 50 newtons, approximately 50 newtons. Then I show that the horizontal force to the left equals the horizontal force to the right. To the left, it is going to be 29 cos of 60. That is to the left. Then to the right, it is still going to be x cos 60. So it is still 29 cos of 60. So these are equal automatically. Then the length of the rod above is 100 centimeters. Determine the force x by taking moments about q. Taking moments about q. So since we know we have to find the vertical component of this, because the length is 100, so this to the vertical is going to be x, or 29 sine of 60. So if I know x to the vertical as 29 sine of 60, then I can use this as 100 as the perpendicular distance. So it means clockwise moments are going to be 29 sine of 60. Perpendicular distance is going to be, even if I take 100, because I know centimeters will cancel out, should be equal to, anti-clockwise moments is going to be 50 newtons times, determine the force x. Okay, we don't know x, but I would simply say x sine 60 instead of 29, assuming we don't know x. So I'll say x sine 60 times 100 is equal to 50. Of course, 50 was at the center, I think. If 50 is at the midpoint, so this is going to be 50 times 50 centimeters. If 50 is the weight of the rod, which is acting at the midpoint. So we just divide both sides by 100 sine of 60. So 50 times 50 divide by 100 divide by sine of 60. So still this gives us x as 28.9, which is approximately 29 newtons. If we take moments about Q, then calculate the magnitude of force F required to balance the rod. So this is anti-clockwise, this is clockwise, this is clockwise. So taking moments about the pivot, for clockwise moments we have F, perpendicular distance is 35 centimeters plus we have 1.2 newtons, perpendicular distance is 25 centimeters, should be equal to anti-clockwise we have 2.5, perpendicular distance is 40 centimeters. Of course the centimeters cancel out, I remain with only newtons. So F is going to be equal to 2.5 times 4 divide by, minus, I'm collecting like terms, so I will say minus 1.2 times 25. 2.5 times 40, that's 100, minus 1.2 times 25 divided by 35, I think that is 2. So F is equal to 2 newtons. I think that is the end of lesson, that should be the end of lesson 4. I think the last lesson is going to be lesson 5, where we shall talk about equilibrium along an inclined plane again. So see you in lesson 5 as the last lesson in force, density, and pressure.